Good morning, afternoon, or evening, depending where you are. I'm glad to be here, starting this morning session of the third day of the meeting, and announcing the first talk of the day by Ana Bravo from Universidad Autónoma de Madrid, with the title on the intrinsic nature of resolution invariants.
So good morning, everybody. First of all, I'd like to thank the organizers for inviting me to this conference and for giving me the chance to present a talk. So here's a brief overview of the contents of the talk. So I work in resolution of singularities. So I will start by defining what resolution functions are. And when defining resolution functions, Hironaka's order function plays a central role. So that will be the second point of the talk. What we have done is we have been able to read this information by using arc spaces. So this will lead us to talk about Nash multiplicity sequences. And even though I know this is a conference about real and complex singularities, please let me talk a little bit about positive characteristic and about what fails when trying to resolve singularities in positive characteristic. This will lead us to talk about the asymptotic Samuel function. So resolution functions. So we all know what the resolution of a singularities is. So given an algebraic variety defined over a field K, we search for a non-singular variety X together with a proper and birational morphism to the original variety. So it is well known the result of Hironaka from 1966, which says that for each variety defined over a field of characteristic 0, there exists always a resolution of singularities. When the characteristic of the base field is positive, we still don't know in general. And there are only results for when the varieties have small dimension. And here's a large list of mathematicians who have been working in this problem. And I hope I'm not missing anyone. There's Biancar, Lippmann, Cossard, Janssen, Saito, Wilpiltant, Benito, Villamayor, Kawanobe, Matsuki, Berlega. But as I said before, I'm interested in algorithmic resolution of singularities. What that means is the following. Given an algebraic variety X, we want to know how to construct the centers that we want to blow up so as to find the resolution of singularities of X after a finite number of steps. The first constructive or algorithmic resolutions were published by Burstall, Millman, and Villamayor by the end of the 90s and beginning of by the end of the 80s and beginning of the 90s. And in addition to providing a constructive resolution, they also simplified Hironaka's original proof. So how do we construct such a resolution of singularities, such a sequence of blowups? Well, this is usually done by defining resolution functions. These functions are defined on each of the varieties in the sequence, and they take values in some well-ordered set. And they have to satisfy some properties. Let me give you a short list. So first of all, we want them to be upper semi-continuous. They have to be defined so that they are constant if and only if the variety is non-singular. The maximum value of each of the functions, which we denote like this, it's always achieved in a closed non-singular subset, which we denote with the underline. And this is going to select for us the center that we want to blow up. In addition, whenever we blow up, we don't want the function to be modified on those points where the blow up is an isomorphism. And finally, the resolution sequence is defined so that at each step, the maximum value of each resolution function has to drop. And because of the properties that I listed here, after a finite number of blowups, will reach a non-singular variety. Okay? So how do we construct resolution functions? Obviously, we need to measure the singularities of the variety. So one possibility is to start by considering the Hilbert-Samuel function. This was in Hironaka's original approach. There is also the possibility of using the multiplicity function. It is possible to resolve singularities, to give an algorithm of resolution of singularities by using the multiplicity, and this is a recent result of Villamayor. Both of these functions, the Hilbert-Samuel and the multiplicity, define upper semi-continuous functions on a variety. However, they are not enough. They don't have all they don't satisfy all the properties that I listed before. So for instance, if we take this surface in A3 and we compute either the top of Hilbert-Samuel locus of the surface or the maximum multiplicity locus of the surface, is the same in this case. It's just a set of points where the order of this function is greater than or equal to 2. This is going to give us this curve, which has a singularity and which is definitely not a center that we want to blow up because it's singular. So usually what we do is to refine either of the previous functions using Hironaka's order function in dimension D, where D stands for the dimension of the variety. So for instance, one could define a resolution function in the following way. At a given point, we can take as first coordinate the multiplicity of the point, and then as a second coordinate, we will have Hironaka's order function. And then there will be other numbers, but all these other invariants that appear here somehow depend on Hironaka's order function. So that's why we refer to this number as the main invariant in constructive resolution. There is also the possibility of constructing a resolution function starting with the Hilbert-Samuel function. So we will have the first sequence of numbers of this function will be the Hilbert-Samuel, and after that we will have also a version of Hironaka's order function in the same way as I wrote here. But for the purposes of this talk, we will be interested in the case in which we are considering the multiplicity as the main invariant. So let's pay attention to this number over here. This is a rational number. We'll talk about this later. But what was the motivation of our work? Well, we know that the Hironaka's order function plays a fundamental role in algorithmic resolution of singularities, but we wanted to know whether it had any other meaning. In addition to that, Hironaka's order function can be also defined over perfect fields of positive characteristic. And we wonder why this invariant is not good enough to lead us to resolution of singularities in general. And this led us to question number 3. There are known refinements of Hironaka's order function when the characteristic is positive, and these refinements of Hironaka's order function are good enough to lead to resolution when the dimension of the variety is small. And we also wonder whether these other refinements have any other meaning expressible in terms of the local information at a given point. So motivated by this, keeping this motivation in mind, let me tell you what Hironaka's order function is. So let's start with a very simple case. Suppose we have an affine variety, an affine hypersurface, but a very particular affine hypersurface. Suppose we fix a ring S, which is a regular K algebra. K is always perfect for us, and assume that the crude dimension of S is D. And I'll take a polynomial of degree M with coefficients in S and define the hypersurface given by this polynomial. And suppose that in addition, the hypersurface has a point of multiplicity M, where M is equal to this exponent. Then observe that all this situation with all these hypotheses, we have in a very natural way a finite morphism from X to the spectrum of S. And this finite morphism has generic rank M equal to the multiplicity. And after a translation of this form on the variable, we can always assume that the coefficients vanish at image by this morphism of the point. So what we will see that here is that Hironaka's order reads information on the coefficients of this polynomial. So for instance, if we were working in characteristic 0, we can always make a change of variables on z so that the coefficient multiplying z to the m minus 1 doesn't appear. In such case, it can be proven that Hironaka's order function is the minimum of these weighted orders, involving the coefficients appearing in this expression. When the characteristic is different from 0, we cannot always perform this transformation. And even if we have an equation with this form, this formula may not be true anymore. But still, we can define Hironaka's order using suitable defined weighted homogeneous functions on the coefficients of the polynomial. This information, these weighted homogeneous functions, are collected into what we call an elimination algebra that we will talk about later in a few slides. And we will see how we will use this elimination algebra to read Hironaka's order. But prior to that, let me add a couple of remarks. The first one is that even though this situation of a hypersurface looks very simple, looks very particular, if we have a hypersurface with a singular point, we can always consider that we are under this situation just by considering some étale neighborhood. But the next question is, what do we do in the general case? How do we manage to measure this kind of invariance in the general case? Well, in such case, we use this result of Villamayor, which we refer to as local presentations for the multiplicity. So for an affine variety X of dimension D defined over a perfect field K, and for a point of maximum multiplicity, what he shows is that there is always, after maybe considering an étale neighborhood, an embedding of X into some smooth V together with functions on V with the following properties. First of all, the functions generate an ideal, which is contained in the ideal of definition of X. And if we look at the maximum multiplicity of each of the functions, which is the maximum order or the maximum multiplicity of the hypersurface defined by each of the functions, then we have this very nice description of the top multiplicity locus of X. It's just the intersection of the top multiplicity locus of these hypersurfaces that we selected in the ideal. And moreover, not only this is true, because in general, in algorithmic resolution, we'll blow up a regular center and we don't expect maximum multiplicity to drop. So what it's nice about this result is the following. If we happen to blow up at a regular center and the maximum multiplicity of x1, the strict transform of x, is the same as that of x, then what Villamayor shows is that the strict transform of these functions still live in the ideal of the strict transform of x1. And again, by using these strict transforms, we have this very nice description of the top multiplicity locus. And that's quite useful in algorithmic resolution because it keeps track, it helps us to keep track of the problem. Now, let me give you an idea on how this smooth ambient space V and how this GR are found, because this is interesting and is related to the previous example that we just saw. So all the arguments we are using are of local nature, so we can assume that X is affine, so X is the spectrum of some V. We pick a point multiplicity M, and then after an étale extension, which we call B prime, it is possible to find a a finite projection of generic rank M to some regular K algebra. So let's write V prime as S by adjoining some elements, whatever elements we need to express V prime as a finite extension of S. Then the GIs that we saw before are nothing but the minimum polynomial of each theta I over S. And then all the information we got in the previous slide, the smooth ambient space is reflected here. The smooth ambient space V we were talking about before is just S where we are adding R variables, R, where R is exactly equal to the number of thetas that we are added here. And then the GIs, together with their weights, are over here. And here's our B prime. And we have this surjection that gives us the embedding, okay? But notice that in the way the maximum multiplicity locus is described, we are using equations with weights. Like we are not paying attention to GI equal to 0. We are rather paying attention to the set of points where each GI has order greater than or equal to MI. So we need to deal with equations and weights. And to deal with this kind of information, we found it useful to use Riesz algebras. So let me tell you a little bit about Riesz algebras and the way we use them in algorithmic resolution. Suppose we have V, a finite type scheme, smooth over a perfect field K. And then we define a sheaf of Riesz algebras as a graded sheaf of algebras with the following conditions. Each IN is a sheaf of ideals. And we are assuming always that G is locally finitely generated. For a Riesz algebra of this form, we can always define the singular locus as the set of points of B where the order of each IN is greater than or equal to N for all N. And this can be shown to be a closed subscheme of B. For each point in the singular locus of the Riesz algebra, we can define the order of the Riesz algebra at that point. And this is given by the infimum of these weighted orders. This infimum can be shown to be a minimum and actually a rational number. So if we go back to the local presentations of the multiplicity, where we have this smooth ambient space, B prime, which happened to be an étale extension of our original ring B, which was representing X. And we look at the equations and the weights. Clearly, if we define the Riesz algebra G as that generated by the GIs in weight MI, what we get is that, by definition, the singular locus of G is exactly the top multiplicity locus of X. But as you can see from the way we found these GIs, this Riesz algebra is not the unique having this property. There are many possible choices of GIs over here, so that we have a nice presentation of B prime over S. And in fact, this will give us different Riesz algebras. So in fact, we could, for instance, replace G by its integral closure in the quotient ring of RW, and this will give us still a nice presentation, a nice property of the maximum multiplicity locus of X. This Riesz algebra G bar will have exactly this property. And we could also saturate G by the action of differential operators in the following form. We could take for each H in weight N in G, and for each differential operator of degree alpha with alpha less than M, we could add to G the result of the action of G over H and placing it in weight N minus alpha. And this will give us another Riesz algebra with the very same property as the one G had. So all these are ways to representing the set that we are interested in. So far, what have we done? Let's summarize. We took a point of maximum multiplicity. We were trying to construct a resolution function. The first coordinate was the multiplicity, which we assume to be M. The second point, in the second coordinate, I told you was Hironaga's order, but so far I haven't defined it yet. So let's define it. Let's review first what we did. We took X and we considered an étale neighborhood. And from that étale neighborhood, we constructed a finite morphism to some regular scheme. And this finite morphism had generic rank M, where M was the multiplicity at the point. This projection gave us an embedding into some smooth B together with a Riesz algebra G. With this information, we are going to construct an elimination algebra, which is going to collect information on the coefficients on the GI. How is this done? Well, we define R to be the intersection of the differential saturation of G with SW. Remember that W is just a variable that helps us to keep track of the gradient. Once we have the elimination algebra, Hironaka's order at the given point is given by the order of this Riesz algebra, this new Riesz algebra, the elimination algebra that we defined at the image of C prime, which was a point mapping to C. So from this diagram, you can see that there are many, many choices. Like we could have chosen different étale embeddings with different projections to some smoothly dimensional scheme of generic rank M, different embeddings to different smooth ambient space and different Riesz algebra G. And still it can be shown that no matter the choice, we always get to the same number, to this Hironaka's order function at the given point. So just to see an example, suppose we select a field to be perfect K, and we look at this curve with a singularity at the origin. So we construct our finite projection to the spectrum of Kx, to the line. The Riesz algebra G is just the Riesz algebra generated by the equation in degree 2. And now we are going to see what the elimination algebra looks like. So if the characteristic of the base field is different from 2, we, after saturating G with the action of differential operators, we get this new Riesz algebra, which is generated by Y in weight 1 and X cubed in weight 2. The elimination algebra is generated by X cubed in degree 2. And Hironaka's order at the given point is 3/2. On the other hand, if the characteristic of the base field is 2, then the differential saturation of G looks slightly different. We'll have X squared in weight 1, while the equation itself in degree 2. The elimination algebra is different too. Is generated by X squared in weight 1, and Hironaka's order is equal to 2. And we wonder what this means. Somehow, if you think about it, I mean, just after blowing up the singular point, we know that we resolve the singularity of the curve. However, this 2 over here is indicating us that it seems we need to blow up twice, which is somehow exaggerating the singularity we are working with. And we wanted to know why this happened. So this led us to study Nash multiplicity sequences. So we studied the arc space of a variety. So let me fix some notation. So we have a variety defined over a field K, and for a given arc, we call the center of the arc the image of the closed point. We refer to the generic point of the arc as the image of the generic point. And the order of the arc at its center is nothing, we will denote it by this symbol over here, dt of the arc. In addition, we use L of X for the space of arcs of X. And for the arcs in X with center a given point, we'll use this other notation over here. So let's look at Nash multiplicity sequences. So they were introduced by Monique Lejeune-Jalabert for the case of a hypersurface, and after all, generalized by Hickel to the case of any variety. And for the purposes of this talk, I'm going to present Hickel's point of view for constructing these Nash multiplicity sequences. So again, we are talking about invariants of local nature. So we are assuming X to be affine. So X is the spectrum of some ring B. We pick a point of multiplicity N, and we select an arc with center at the given point. Now, from this arc, we construct this other arc. And geometrically, what we are doing is we are taking the singular point that we had, and we are multiplying by a line the original variety. So we are distributing the singularity along a whole line. Okay, with this new arc, we have a center, which is given by this point. And this new arc is going to determine a sequence of blow-ups. So we blow up at the first center, we lift the arc to gamma 1. We look at the center, we blow up the center, we lift the arc, and so on and so forth. So this is going to give us a sequence of points. And we look at the multiplicity of each of the points appearing in the sequence. So this sequence of multiplicities is what we refer to as the Nash multiplicity sequence of the arc. This sequence is going to be a non-increasing sequence of positive integers that starts with the original multiplicity and stabilizes at multiplicity of the generic point of the arc. And somehow, intuitively, we can think about these numbers as the multiplicity of the original variety along the arc that we fixed at the beginning. Okay, so with the previous data, we have X, which is the spectrum of some ring. We fix an arc with center the given point of multiplicity M. We paid attention to the Nash multiplicity sequence of the given arc. And in special, we pay attention to the very first time the Nash multiplicity sequence drops below the original multiplicity. And we call this the persistence of the arc. Now, it is clear that the larger the order of the arc is, the larger the persistence will be. To get rid of this influence, we normalize the persistence by dividing by the order of the arc. So what is the persistence measuring? Well, remember, we have a variety with a singularity, and we multiply by a line. So we distributed all the singularity along the line. Okay, and then we leave the arc, and the arc now is touching at this line at some point, which that's the center. We start to blow up, and the persistence is counting how many times I need to blow up to separate the arc from that line that I obtained at the beginning. So with this persistence and normalized persistence, what we proved together with Santiago Encinas and Beatriz Pascual Escudero is the following result. Given a variety of dimension D defined over a perfect field and a point of maximum multiplicity, then the normalized persistences are always bounded below Hironaka's order. And in fact, we can compute Hironaka's order by studying the normalized persistence of some very special divisorial arcs. In fact, in particular, studying divisorial arcs that define Riesz valuations at the point. So if we go back to our example, that the one of the cuspidal curve, and we assume, for instance, that the characteristic is positive, where we obtained that Hironaka's order was 2, and we thought it was a little bit too much. What happens here is that there are no normalized persistences below 2. There's no way to separate the arc from the line in less than 2 steps. And in addition, our result says that Hironaka's order can be computed in any characteristic by studying the arcs of X which center the given point. Now, what fails in positive characteristic? Why is this order so high after we saw in the example? Well, let's go back to the hypersurface case. Let's go back to the simple case in which we assume that X is a hypersurface defined by a polynomial in degree M with coefficients in some regular S. Well, remember, we defined the Riesz algebra generated by the equation itself in degree M, and from that, by taking the differential saturation, we defined the elimination algebra, which was supposed to be collecting information about the coefficients. But somehow, when the characteristic is positive, the elimination algebra fails to collect all the information coming from the coefficients. In such situation, this is what I'm going to talk about now is a result of Benito and Villamayor. They have the following idea. For a given equation like the previous one, let us collect the information coming from all the coefficients. And let's define the slope of such an equation by the minimum of these weighted orders together with the order given by the elimination algebra, Hironaka's order. Obviously, this is not an invariant because if we make changes of variables on the variable z by translating with elements in the base ring S, we'll get different slopes. So what they do is they consider all the possible translations on the variable, and they define the H order at a given point as the supremum of all the possible slopes. And they show that, in fact, this is a maximum. Okay? So if we go back to the example of the cuspidal curve, well, remember we have this elimination algebra in characteristic 2 with Hironaga's order equal to 2. In this case, it can be shown that the H order is 3/2, which is below 2, and it's exactly the same invariant we got when the characteristic was different from 2. So what Benito and Villamayor show is that it is possible to define the H order for any variety. And to this end, they prove a very beautiful generalization of Weierstrass's preparation theorem. And to prove that the H order is defined for any variety, they need to use neighborhoods of a singular point, and they need to consider general projections to smooth the dimensional schemes. In addition, they prove that with this invariant, they have enough to prove resolution of singularities for surfaces. So after seeing their invariant, we wondered the following questions. We formulated the following questions. We wanted to know whether we could read the H order directly on the local ring. And the answer will be yes, as we are going to see. And to do so, we'll need to study, as before, the space of arcs which center the given point and the cotangent space at the point. And the next question was, does this H order have any other interpretation in terms of the algebraic properties of the local ring? And we will see that the answer is yes. And to do so, we'll use minimal reductions of the maximal ideal and the so-called asymptotic Samuel function. And this is work in progress with Angelica Benito and Santiago Encinas. And let me tell you a little bit about it. So the asymptotic Samuel function. So suppose we fix a local ring, then with maximal ideal M. Then for each element in A, we define the order of this element by looking at the supremum of the powers of the maximal ideal where the element is contained. With this, we can define the asymptotic Samuel order, which we shorten by S order at the given element, by taking this limit. So this S order has the following properties. It can be shown to be either infinity or a rational number. It has the expected property when taken over the sum of two elements, and the expected property or almost expected property when computed on the product of two elements. When the ring is regular, it can be shown that this S order is equal to the usual order at the regular local ring. And before going forward, let me tell you that this order can be defined for any ideal in any ring. We just have chosen the case of the local ring because that's the one we are interested in. Okay, when the ring is Noetherian, it can be shown that the S order of an element is above n over L, where n and L are positive integers, if and only if alpha to the L is in the integral closure of the nth power of the maximal ideal. In addition, again, when the ring is Noetherian, if we call V1 to be a set of Rees valuations at the maximal ideal, then it can be proven that the S order of an element is given by this minimum, where we compare the valuation of Vi at the element to the valuation of Vi at the maximal ideal. Again, if we go back to the example of the cusp, we could compute we could consider the maximal ideal of the singular point. And if we compute the S order of the class of X, we get 1, while if we compute the S order of the class of Y, we'll get 3/2. And in fact, Y squared lives in the integral closure of the ideal generated by X cubed. On the other hand, X generates a reduction of the maximal ideal. Okay, So the asymptotic Samuel function defines a natural graduation in the ring by considering the following ideals. So for each T positive rational, we can define the ideal of all the elements where the S order is greater than or equal to T. And we can also consider this other ideal where we are collecting all the elements with S order greater than, strictly greater than T. This gives us a graded ring, which we can compare to the usual graded ring of the local ring. So there is a natural morphism from one to the other, and it has a kernel. The kernel is the set of elements in the graded ring of A, which are nilpotent. And these elements, the elements in the kernel, they all come from elements in the original ring whose ordinary order was n and whose Samuel order was greater than n. So for our interest, we are going to be paying attention to this morphism in the particular case in which we are considering the local ring of a variety at the singular point. So we have this map from the ordinary graded ring to the one given by the Samuel function. And we pay attention to the degree 1 part. So we call lambda to the restriction of delta to the degree 1 part. And the first thing we observe is that any minimal set of generators of the maximal ideal is going to contain at least d elements of Samuel order equal to 1. And therefore, if the embedding dimension at the singular point is d plus t, remember that d was the dimension of the variety, then what we have is that the dimension of this kernel is going to be bounded by t. And our goal is to study the dimension of and the elements that are in the kernel of this map. So first we show that when the dimension of the kernel is not the highest possible, then the H order is 1, and moreover, Hironaka's order is 1. So in this case, we can compute Hironaka's order function even without needing to look at the space of arcs which center the given point. In addition, the fact that this order is 1, at least when the characteristic is 0, is an indicator, indicates that lowering the multiplicity is a problem that can be solved in dimension d-1, which somehow indicates it's a simpler problem, but I'm not going to go into that. So what happens in the case in which the kernel has the largest dimension possible? So we are at a singular point of a given variety x, which has dimension d. We are assuming that the embedding dimension is d plus t, and we are assuming that the dimension of the kernel is the largest possible t. So first of all, we observe that even in the case, we could be in the case in which we are working over a point where the residue field is finite. Even in that case, we can show that the maximal ideal has a reduction generated by the elements of S order 1. So what we do is we choose minimal sets of generators of the maximal ideal of the following form. We take D elements of S order 1 and then T elements with S order larger than 1, which induce a basis of the kernel of lambda. For each of these choices, we look at the minimum of the Samuel order of these elements. So this minimum, this delta B, is measuring how deep the ideal generated by the theta I lies in the integral closure of the maximal ideal, because remember that these elements generate a reduction of the maximal ideal. So once we have this delta B, what we do is we define the slope of the ring as the supremum over all the possible choices of elements of this form inducing a basis of the kernel. This will be the slope of the ring. And with this, what we show is that the H order at a given point, this is a result with Angelica Benito and Santiago Encinas, we showed that the H order at a given point is the minimum between the slope and Hironaka's order function. So summarizing, the slope can be read using information from the cotangent space, and Hironaka's order can be read by looking at the arcs in X which center a given point and the risk valuation at the maximal ideal. And in this case, with this strategy, we don't need étale extensions, we don't need embeddings, we don't need to find finite projections to any smooth variety, because all the information is already in the local ring of the point or in the space of arcs with center the given point. And this is all what I wanted to say. Thank you very much for your attention.
Well, Anna, thank you very much for your nice talk. And now is the time of questions. So let's wait for questions from the attendants. So far, I cannot see any questions here in the chat, but I don't know if I'm doing right things or not. So, okay. Here is some questions. I don't know what, can you see it?
Yeah, is the persistence of an arc related to Hirnaga's notion of maximal contact? I think there is a way to detect maximal contact by studying the persistences, because somehow, if you find a hypersurface of maximal contact, there is this is a hypersurface that is going to be any arc is going to have a center in this hypersurface along its Nash multiplicity sequence. So somehow you can use the Nash multiplicity sequences to try to find hypersurfaces of maximal contact in characteristic 0. I don't know if this answers your question. That's a good question.
Waiting for more questions. Well, I cannot see any more questions so far, so I think we can thank the speaker for
Thank
this.
You.
Talk.
Oh, there's another question. What fields on the invariant H order for dimension greater than 2? Well, what happens, it doesn't give you enough information again. So again, you have to look for more refinements. So the H order is giving you some information, but you have to fill in. You have to look for new invariants. Why do you need to take the integral closure of the maximal ideal in your argument? I don't know in which part you mean. Yeah, the maximal ideal is integrally closed, but I think, what do you need to take the integral closures of the maximal ideal? Because no, it's not the integral. It's not as much looking at the integral closure of the maximal ideal, but looking at powers of the maximal ideal and then taking the integral closure. I don't know if this answers your question. Maybe I'm not getting what you were asking. Sorry. H order is not approximately continuous. Does this also an instruction? This I don't know. I'm sorry. I don't know if this is an abstraction, but definitely you need more information. I don't think the H order is enough to pursue singularity, resolution of singularities. You need more.
Carmen, I think that's it.
So okay, I think we can close this talk now. Thank you very much, Anna.
Thank you. Thank you very much for everything. Bye.
Bye-bye.
Greetings, everyone. We'll be back at 10 past 10. See you.
Okay, welcome everyone to this edition, 16th International Workshop on Real and Complex Singularities. It's such pleasure to introduce the next speaker, Professor Jörg Schürmann from the University of Münster. It's an honor and pleasure to introduce Professor. Please go ahead.
Okay, thank you for the introduction. I hope you can hear me. I don't have a picture at the moment. And of course, thanks for the invitation. It's a very great honor and a pleasure to give a talk in this wonderful meeting, especially this celebrating 30 years of São Carlos workshop on real and complex singularities. So the title of my talk is Non-Characteristic Pullback Formula for Motivic, Churn and Hirzebruch classes, but I don't expect that most of you maybe know about what it is. And even if there are some experts in the audience, I decided to first start with a general introduction to this kind of subject. So the subject is about characteristic class of singular spaces. This is a subject I entered maybe almost 20 years ago, and I give an overview about the 5 known functorial characteristic classes of singular spaces. This is the first part of the talk. In the second part of the talk, I explain a little bit how these things are related to nearby cycles, so which has to do with Milnor fibration information in a global way. And this is needed in the end for the last part of the talk, where I want to come to the new result, which I want to explain with some applications. So I want to present you an overview of functorial characteristic class of singular spaces. So there are 5 examples known, which I explain in a moment, and they all have the same calculus, which I want to explain. So I don't want to explain to you technical details, but I want to show what is the calculus working for all of them. And maybe I should say there are other characteristic classes, very important one, like the elliptic classes of Totaro, Lipkova, and Borisov, which don't fit into this functorial view. So that will not appear here. So a functorial characteristic class is a transformation from some theory to homology. So the big difference to characteristic class of vector bonds is that characteristic class of singular spaces live in homology. For this talk, I restrict to the complex algebraic context, so that you can always choose if you prefer a topological viewpoint or an algebraic geometric viewpoint. Both is possible in most situations. And here are the properties one usually expect for this kind of transformation. So transformation means it's functorial for proper morphisms. So this is very important. It means that these characteristic classes are always designed to fit with mapping situations. So even if the ambient spaces are smooth, but the map is singular, these characteristic classes can be highly interesting and are especially designed for this kind of situations. But to speak of a characteristic class of a space, you need to apply this transformation to something. So you expect there's a distinguished element in the theory. And the theory question mark really depends on which characteristic class you are using. You will see in a moment. And to speak of the characteristic class of your space, you need to choose a distinguished element. And then you define the characteristic class of X as a transformation applying to this distinguished element. And maybe already in the beginning, I should give you a warning that there are usually for singular spaces, there are different choices of this distinguished element. And only for smooth, they are all agreed. If you don't know about characteristic class of singular spaces, at least you should look at their degree. So if the space is compact, you can push forward this class to a point, and this is a degree of X. And that you should think about as a sort of characteristic number, extended from the smooth context to the singular context. And in the smooth context, if your singular space is especially smooth, then of course the tangent boundless available and Poincare duality is available. And you think about that the class of your smooth space is just the class of the tangent boundary evaluated on the fundamental class, so that you can view this as an element of the homology. And the characteristic classes we are looking for are multiplicative ones, so they are always defined by power series in the Churn rules. And it is really this normalization condition which gives the name to the characteristic class. So the next example I will show you are Churn classes. So Churn class of singular spaces comes from the normalization of Churn class of smooth. So this is always where the names comes from. And this is the basic calculus. And there are two additional properties which are fulfilled in all examples. So one example is the multiplicativity of these characteristic classes. So they commute with a cross product if you are working on a pair of spaces. And it's a good exercise for you to figure out what this kind of formula means if you're in the smooth context. It's just the splitting of the tangent bundle of a product. But this property holds even for singular spaces. And similarly, we have what is called the Riemann-Roch theorem for submersion. So if you have a submersion of singular spaces, you have a pullback map in homology. And so you can ask, how are these characteristic classes behaved under pullback and submersion? And downstairs here, you find the expected formula. So the shape of the formula is very simple because you can figure out what should it be in the case if x is smooth. If x would be smooth, x prime would be also smooth. You pull back the tangent bundle and you want to compare this with the tangent bundle of x prime, and you see the difference is the tangent bundle to the fibers, and you expect that exactly this correction factor, the cohomological characteristic class of the tangent bundle to the fibers, should measure the difference between these terms. And the statement of the Riemann-Roch formula is that this expected formula even holds in the singular context. So these properties hold now for all examples I will now give to you. The first and maybe simplest examples are Chern classes of complex singular spaces, which maybe here in Brazil and Mexico are the most well known, and especially in San Carlos, of course. We have seen this in the talk on Monday by Xi Ping, who mentioned Chern classes. And for sure, Jean-Paul and people, they gave a lot of summer cool lectures on this. And I had the chance 2 years ago in the last conference in Sao Carlos to give a lecture course on McPherson Chern classes. So this is a theory going from constructible functions either to Chow groups or Borel-Moore homology, depending which language you prefer. And the push forward of a constructible function is by taking the Euler characteristic of fibers. And the distinguished element you usually would expect is the simplest you can choose is just the function 1. And if you apply this transformation, then you get what is called the Chern-Schwarz-McPherson class, because McPherson introduced this Chern class transformation, but Marile and Schwarz introduced this characteristic class of the singular space already many years before, and later on they showed they agree. But maybe here's the easiest example to show you that there are different choices of distinguished element. So if x is pure dimensional, you can also choose the Euler abstraction here. And if you then evaluate this, you would get the Chern-Maser classes. And Euler abstraction also showed up in several talks here. Yesterday, for example, in the talk of Una. So for the distinguished element, you have choices, but here we take the most natural one, which is the function 1. Then the degree of this characteristic class is just the Euler characteristic by this definition of the push forward. And in the smooth case, the Chern classes are just defined by this power series. So this is the first example. And historical, the examples came also in the timeline in this order I present you. The next example, or maybe here I should make the remark because this is a conference on real and complex singularities, and maybe Clint is also in the audience. So there's a counterpart in real geometry, where instead with integer coefficients, you work with more two coefficients. And these classes are these Stiefel-Whitney classes originally introduced by Sullivan in terms of PL geometry, and later recovered and restarted to study by Fu and McCrory. So they are a strong analog in real geometry. But most of the other characteristic classes I'm using really need complex geometry. So the next example is the Todd class transformation of the singular Riemann-Roch of Baum, Fulton, McPherson. So this is a transformation from the Grothendieck group of coherent sheaves to Chow groups or homology. And here it's important that you work with rational coefficients because localized Chern characters are behind the construction. And the push forward on Grothendieck level is by taking alternating direct image sheaves. So this is this invention of Grothendieck. And then if you want to choose a distinguished element, I think the only natural coherent sheaf you are thinking about is the structure sheaf of your space, and then you get the Todd class of X. If you push forward this to a point for X compact, you see this time you don't get the topological Euler characteristic, but this time you get the holomorphic Euler characteristic of your space. And the Todd class for the tangent bond of the smooth space is defined by this famous power series invented by Hirzebruch when he came to his invention of his Hirzebruch-Riemann-Roch theorem. And this is the generalization of this to the relative situation for singular spaces. The last examples, which were known in the Churn class and Todd class, was developed in the 70s. And I think the third example, L classes, were developed in the 80s. So this is the L class transformation of coupled-Chennescent and by a different construction on Wolf. And this works for perverse sheaves or self-dual constructible sheaves. So Witt groups are an analog of Grothendieck groups if you have a duality floating around. And the duality you have floating around here is Verdier duality for constructible sheaves. And then you can look at self-dual objects which are symmetric or antisymmetric. So this plus minus in the index just means you look at symmetric or antisymmetric objects. And the L class live on these Witt groups and codify signature information. And these Witt groups of the triangulated categories agree with the Witt groups of perverse sheaves, which is an abelian category, which is maybe a little bit easier. This was a recent result which I proved by Wolf, which is in the background here. In this context of L classes, I think Markus Banagel gave 2 years ago in this conference an overview about the history and the development of these kind of things. And maybe this is the most complicated characteristic class. The distinguished element, what you want to pick is you want to have something which has Poincare duality on a singular space, and this is where intersection cohomology comes in. So we take intersection cohomology with middle perversity to get it self-dual. And the L class, which you get if you evaluate this transformation intersection cohomology, this is the L class introduced by Gowreski-McPherson. And originally, if you only work with rational homology manifolds, this is the oldest characteristic class of singular spaces, then you don't need intersection homology. And then this is just a Tom class introduced by PL geometry for rational homology manifolds. I should say this L class is a purely topological theory. So this does not take values in Chow groups or something. You really need the spaces compact. And these are homology classes because they are defined by the signatures of fibers mapping to spheres, something non-algebraic. The degree is the signature for the intersection homology pairing, and the L classes in the smooth context are defined by this power series. So these are the 3 characteristic classes which exist in the 70s and in the 80s. And as I want to emphasize here, they have a very similar calculus. Also, the geometries they codify are completely different. So so one is topological Euler characteristic, one is holomorphic Euler characteristic, and the third one is about Poincare duality or duality questions and signatures. But still, they have all the same calculus. So the natural question is if one can unify these things, and that is what I could do in joint work with Jean-Paul Brasselet and Shoji Yokora many, many years ago, maybe 15 years ago or something. We created the theory of Hirzebruch class transformations, which allows to unify these 3 different characteristic classes, which is not so easy because they live in homology. So the trick coming from something Hirzebruch has done in the smooth context is to develop a characteristic class transformation which has a parameter y in between. So this parameter y will be very important if we want to specialize to special values to compare in a moment with the other 3 characteristic classes. And it turns out the simple presentation of these Hirzebruch classes is they live on Grothendieck group of varieties. So here you look at isomorphism classes of maps, and you divide out the cut and paste relation. So if you have a smooth, a closed subset, the class of the closed subset and the open complement is the same as the class of the space. So this is a sort of additivity property, which is very similar to the additivity property of Churn classes in terms of constructive functions. And I would propagate these relative Grothendieck group of varieties you should think about as motivic constructible function. So this is a Richer theory, so this allows a Richer transformation. And this Hirzebruch class transformation comes in 2 versions. So there's the one without head, this is the unnormalized version. And with the head, we have to renormalize by some powers of 1 plus y. So if you are on degree star, you multiply by 1 plus y to the negative star. So this is just a renormalization, which becomes important if you later on want to plug in y equals to -1. Otherwise, you can go between both transformations forth and back. Okay, And for this transformation, what are the distinguished element? If you play with arrows, the only distinguished element you have is the identity arrow. And if you evaluate this transformation on this identity arrow, you get what is the Hirzebruch class, or if you make this with the renormalization, this is the normalized Hirzebruch class. Its degree for a compact space is called what is the chi-y genus of X. So this is a one parameter characteristic number. And if the space is smooth, the Hirzebruch class is defined by this power series. And you see the trouble with this power series, which comes from Riemann-Roch, is if the constant coefficient is not 1, as you usually do, so this is not a normalized power series, but it starts with 1 plus y. And if you want to catch this chi-y genus by a normalized power series starting with 1, you have to make this renormalization trick that the Churn root is multiplied by 1 plus y, and you plug this into the power series. And then again, you divide by this 1 plus y. And this is on the homology level upstairs, exactly this renormalization you have to do. This will be the unifying characteristic class living in homology, which includes a parameter, which in a moment will be very important to compare this to the other three characteristic classes. It turns out in the construction of our characteristic class, we could even introduce a k-theoretical version. So up to now, these characteristic classes lived in homology. And in our construction, it turned out we even can go to k-theory and then apply Riemann-Roch. And this k-theoretical version, which is the most richest and maybe the most important characteristic class nowadays, we call it the motivic Churn class transformation. And there are two versions. So for most of the talk, the motivic version would be enough, but there's also a version which factorizes over a Grothendieck group of mixed Hodge modules, which you should think about as a sort of kind of Hodge sheaves. And we will see in a moment why this is at one point very important. So if you apply this motivic Churn class transformation, it has all these formal properties I started my talk with. The distinguished element would be again the identity arrow if you do this in the motivic level. And in the Hodge level, that would be the constant Hodge sheaf, which is so simple to write as Qx with an index upper h, but which is a very, very complicated object to work with. Again, the characteristic class is the same, the degree is the same as for the Hirzebruch class. This is a chi-y genus, and at least for a smooth space, you can now see what the chi-y genus is, because the characteristic class of a smooth manifold is the characteristic class Hirzebruch looked at, is the so-called lambda class of the cotangent bond. So you look at all classes in the Grothendieck group of coherent sheaves of different algebraic or different holomorphic differential forms. And the parameter y is just the counting parameter in which degree you are. And you see the chi-y genus is just collecting all these holomorphic Euler characteristics in the smooth case. And in the singular context, this is an extension of this definition to the singular context. So these are the 5 characteristic classes which exist for singular spaces in complex world and have these functorality properties. And now I want to explain what is the relation between these characteristic classes, why they are so similar. So as I pointed out, the motivic characteristic class going to K-theory is the basic one. And from this, by applying the Riemann-Roch transformation, this is the Todd class transformation. By applying the Todd class transformation, we get the homological version, and which is the shadow of this, and the homological version was the Hirzebruch class. And you get this unnormalized version just applying Riemann-Roch, and if you make this renormalization, you get the normalized Hirzebruch class. In a moment, I want to compare this motivic level, for example, with Euler characteristic information used for Churn class transformation. And here is that there's a tautological arrow from the Grothendieck group of spaces to constructible function, which you can factorize in between by a Hodge level. You can go to mixed Hodge models, or from the mixed Hodge model, you can go to constructible sheaves by taking the underlying rational constructible sheaves. So you can, in the end, work here on 4 levels: motivic, Hodge theoretical, constructible sheaves, or constructible function. And all together, they give you a natural arrow from this motivic constructible function to usual constructible function. And this arrow comes up if you want to compare the Hirzebruch class with the Churn class. So now you go to the left side of this commutative diagram. If you plug in the special parameter y equal to -1, then the normalized, and here it's very important to use the normalized Hirzebruch class. The normalized Hirzebruch class just compares to the usual Chern-Schwarz-McPherson class, but here everything with rational coefficients, because this theory needs rational coefficients. So for the parameter y equal to -1, this compares to Chern class transformation. For the other parameter y equal to 0, it really compares to the Todd class transformation. And here the error is just coming from a special evaluation of this motivic Chern class transformation. And so in this sense, this Hirzebruch class transformation, the normalized version, unifies Chern and Todd class transformation. And this was our original motivation. So as a transformation, this unifies these theories, but you have to be careful. If I want to compare the characteristic classes of a space, I still have to use a distinguished element, and they don't need to fit always together. But in some cases, this works. So for example, for Chern classes, it always works. So the Chern class always fits with the Hirzebruch class. And if you take the normalized Hirzebruch class for y equal to -1, you really get all Chern classes with rational coefficients. And here you now see why this renormalization is needed. If you would do this without the renormalization, you only would get the degree 0 Chern class. So that is where this renormalization comes in. Otherwise, this is not important. So for Chern classes, it always fits. For Todd classes, the Todd class of X fits the Hirzebruch class, which is normalized Hirzebruch class as a parameter y equal to 0, if the singularities are not too complicated. So if the singularities are Dubois, because this has to do with Hodge theory, which is behind the scene. So for example, this is okay for rational singularity. So for these parameters, y equal -1 and y equal 0, everything is understood, but there still is a third parameter where not everything is understood. And the third parameter is if you plug in y equal to 1. And so here we formulated with Brasselet and Jokora our conjecture that if you evaluate the normalized Hirzebruch class on the corresponding intersection homology Hodge module, and this is why we need the Hodge version. Intersection homology does not exist up to now on a motivic level. And here we are forced to work with a Hodge level to really speak of intersection homology versions of these transformations. And here we expected that if we apply our transformation to the intersection homology complex suitably normalized, then for the parameter y equal to 1, the third important parameter, this should fit with the third characteristic class with the L classes. And this is a conjecture. One should say for projective singular spaces, its degree is proved by Saito's famous Hodge index theorem for the intersection cohomology, which extends to the singular context the Hodge index theorem for Kähler manifolds. And most recently in this year, Bobadilla and Paleris could prove that this conjecture is true at least for rational homology manifolds. Okay, so this is the relation between these different characteristic classes. And now I want to go to the second part. So up to now, I presented the basic calculus. And now in the second part, I want to go to nearby cycles which has to do with specialization. So nearby cycles codify something which has to do with Milnor vibration information. And this you put along a singular support. So here we work usually with non-isolated singularities. And these nearby cycles codify this Milnor information, local Milnor vibration information along a hypersurface given by an equation G. And the vanishing cycles measure the difference between special and nearby fibers. And this slide, I'm very fast on this, so I only said to you, for the intersection homology version, we need this very complicated mixed Hodge models on Saito. And just think of them about these are sheaf versions, or these are constructory sheaves with Hodge properties, because on the point space, they give you polarizable mixed Hodge structures. And the important thing is you have all functors, which are listed here. And in a moment, I want to come to nearby and vanishing cycles. And because you have all functors on the scene, it means if you with these functors could create some coefficients, you can always do this with on the Hodge level. And maybe here I'm a little fast and just say you get this constant Hodge module by taking the constant Hodge structure on a point. It's just a Tate Hodge structure without a twist. You take a pullback functor by a constant map, and then you have this constant Hodge sheaf on a space. But similarly, you can introduce using functors and perverse T structure, you can create also the intersection cohomology Hodge module, which is so important if we want to compare with L classes. Okay, so now forget about Hodge modules, just believe there's a Hodge version of our theory. And now I want to go how these characteristic classes compare to, or how they behave under nearby cycles. And you should see, as the title of the page shows you, we have 3 levels. We can work on a motivic level, on a Hodge level, or on a constructible level. So we take a global morphism of function on our singular space, and we assume that the special fiber is of codimension 1. And in the motivic language, we need this Lefschetz class of the affine line. And then we have this kind of nice commutative diagram. And we start here with where Delin's name is attached. So from the Grothendieck group of constructible sheaves, we have this famous nearby and vanishing cycle functors attached to this function G, which were introduced by Delin. And if you only look at the Euler characteristic information, looking at the Euler characteristic stalks, Verdier in the 70s showed that you similarly get a nearby and vanishing cycles on the stalk level. And maybe this is the simplest we have seen in some talks already, not in this language. But what it means, if you evaluate this on a point, means you take the Euler characteristic of Milnor fibers. This is behind this language of nearby cycles. And upstairs, it's just to know there are a Hodge version of this by Moriko's Saito language, and there's even a motivic version introduced by Denner and Löser. And maybe this is, of course, in the beginning, very surprising that you have Hodge and motivic version of these local transcendental Milnor fibers. But just believe you have this transformation also on a Hodge level and on a motivic level. And on a Hodge level, you always need to introduce a shift to fit with the Delin definition. That is why I introduced this prime. So this is just a sign question on Grothendieck groups. So this picture should show you have nearby cycles and even also vanishing cycles on 4 levels: motivic, Hodge, Delin's level, and classical Verdier level for constructive function, and you can compare them. And now we asked, how do our characteristic classes behave under this kind of nearby cycles? And the thing is, if I have a global hypersurface, I have a similar Gaussian map on Chow groups or homology or K-theory. And so it makes sense to compare this with the pullback of the characteristic classes. And let's start here with the top level. Here's a result I could prove maybe 10 years ago or something. So the highest level, the motivic Churn class, so you should read this formula in the following way. You start on the Grothendieck group of mixed Hodge in the Hodge level, for example, on the ambient space and go to the hypersurface. And then nearby cycles commute with this transformation, motivic Churn. If you, on the homology side, takes a Gaussian map, but here for the motivic Churn class, there's a power 1 plus y appearing, which looks a little bit surprising. But the reason why this power 1 plus y has to appear is because this is the characteristic class of the normal bundle. So if I have a global hypersurface, the normal bundle is trivial because I have an equation. But still, the lambda class of the trivial line bundle is 1 plus y. And this is why this factor 1 plus y has to appear in the theorem. And so this theorem I proved some years ago that motivic Churn class commutes with specialization. That would be a good phrasing for the theorem. And from this, you can get as a corollary that the same is true for the Hirzebruch classes, for the normalized Hirzebruch classes. They commute with specialization. In homology, you take Gaussian map. For motivic or Hodge version, you take nearby cycles. And if you evaluate this on the constructive function level, so on the lowest level, just the Euler characteristic level, this fits with an old result of Verdier that the Macpherson Churn class transformation commutes with specialization. I think this was proved by Verdier also in the 70s. And you should think about the other results above, that there is an Hodge version and a motivic version of this classical result of Verdier. So these characteristic classes are also very natural if it comes to the viewpoint of one parameter families, and you look at the specialization in one parameter families. As long as in the coefficient you use nearby cycles, which look at a nearby fiber, this fits nicely with the Gaussian map on homology, because also Gaussian map is defined by nearby fibers. And this is a general calculus available some years ago. And so almost everything on the foundation of the calculus of these characteristic classes was now available and holds for all these 5 characteristic classes. But in recent time, we came to application of these characteristic class transformation. And it turns out that one final result was missing in the literature. And this is a basic new result, or most recent result, I want to explain now in the last part of my talk, which has to do with a non-characteristic pullback. So in the third part, we want now discuss how these characteristic classes behave under pullback in a higher codimension situation. And to be available to pullback homology classes, we need ambient smooth spaces. So here my singular space X is sitting in an ambient smooth space, and we want to intersect this with a submanifold of the ambient smooth space. And then the intersection of the singular space will be another singular space X prime. And the normal boundary of the submanifold, I call it in this way. And because we have this ambient smooth manifold, there are Gaussian maps. In topology, that would be just come from Poincaré with support and so on. But using these ambient manifolds, one really has even a Gaussian map for singular spaces, which otherwise would not be available in homology. And then the natural question is, how do these characteristic classes behave under this pullback to intersection with a submanifold? So the formula one would expect, if everything would be a smooth manifold, the formula would be of the following type. So you want to compare taking first the characteristic class and then pullback, or first pullback and then the characteristic class. And the correction term should be just the cohomological characteristic class of this normal bond. But the question is this formula true? So in the smooth context for transverse intersection, it is true. But as it turns out, if you go to the singular world, it is not always true. So one has to find conditions and ask under which conditions this formula might be true. And this has been done over the time now for the 3 original characteristic classes in the following way. So for the top class transformation, this was already proved by Verdier in the 70s, 80s, and here it's always true. So for the top class, there's no question, you don't need conditions. And the reason for this is that the top class transformation is a transformation of 2 homology theories, which is not true for the other transformation. So for top class transformation, this refined intersection formula is always true. So the next thing which was studied is what happens for Chern class story. And here I proved some years ago this formula is true for Chern classes if you have a sort of transversality condition, which I proved under a slightly weaker condition than transversality to a witness stratification, which is a non-characteristic condition I will explain in 1 minute. But maybe I should point out you need a condition. If you don't ask conditions, this formula is wrong. And usually the difference term, which is measured, has to do with vanishing cycles and has to do in the Chern class story with Milnor classes. So what I want to present here today is now a context where you ask the condition where no vanishing cycles appear, so no Milnor classes appear, and it turns out some sort of transversality condition is enough, and this will be the non-characteristic condition. And then this formula is true for Chern classes. And the most recent result was proved by my friend Markus Bannagel, I think just this year, that he proved a similar formula is also true for the L-class transformation, at least if you apply it to the distinguished element, the intersection cohomology complex. And here you really ask that the submanifold is the transversal to a witness stratification of the singular space. So you see transversality or non-characteristic. If you have good conditions, this formula is true for Chern class and L classes. And now I should explain what these non-characteristic mean, because it is a language coming originally from microlocal geometry, coming from D-model language. So what is this non-characteristic condition? So one looks at the cone, so it's just in the cotangent boundary. So you look at the closed cone, this is just a C star invariant subset, and the submanifold is non-characteristic for this cone if you intersect this cone with a conormal, so this T star M prime M, this is a conormal boundary. So these are all holomorphic one forms. If you restrict them to the submanifolds, they vanish. So this is a conormal boundary. And the non-characteristic condition means if you intersect this cone with a conormal boundary, then it should be in the zero section. So this is a non-characteristic condition coming from microlocal geometry, from D models. And to give you a feeling for this, this is a weaker condition than transversality, which maybe it's more geometric and most people of you maybe know. So let's, as an example, assume X is a singular set in an ambient space endowed with a witness stratification. And the cone you should look at is, you look at the conormals to all strata. So S are the strata, and you look at the conormals. So these are even subvector boundaries in the cotangent boundary. But this is usually not a closed set. And only if you take them all together, this is a closed set by Whitney A condition. And this will be a cone, so a C star invariant subject. And if you now ask that a submanifold is non-characteristic to this cone, it's just a reformulation that this submanifold is transversal to all strata. So if you ask this non-characteristic condition for all conormals to strata, this is exactly transversality. But otherwise, it could be weaker than transversality to witness stratification. So for example, if we do this in the context of Chern classes, if we take a constructible function, which is locally constant on the strata, there's a series of characteristic cycles. And then you have to look at the support of this characteristic cycle. And this is again a cone in the cotangent boundary, which is supported on the conormals to the strata, but it could be much smaller. So to ask to be non-characteristic to this cone is weaker than asking to be transversal to the witness stratification. Still, it's enough to imply this expected intersection form. And the example which I now need in the next slide is, if we take a perverse sheaf, or if we work with a Hodge version, if we take a mixed Hodge model, and then the cone we would like to look at has different descriptions. Everything is supported on the conormals to the strata. So if a submanifold is transversal to the stratification, it will be automatically non-characteristic for this cone. And for this cone, you have now three different descriptions, which all gives the same. You can just say, if you take the constructible function associated to it, it would be the support of the characteristic cycle. You could also say, this is a singular support in the language of Kashiwara-Shapira of the associated perverse sheaf. Or you can say, this is the characteristic variety of the underlying D module of a mixed Hodge module. So all gives the same cone, and you ask now this non-characteristic property for this cone. And here comes now the new result, which was expected. And many people asked me about this. And the thing is, I now have to write it up and to give a proof, because it's really needed for some applications. And so I just want to propagate this here. And but this is still in progress. I still have to write this up. So everything is available, but still I have to find time to write this paper. So if this submanifold is non-characteristic to this cone I presented in the slide before, and you can use maybe the easiest language is the support of the characteristic cycle of the corresponding constructive function, then these expected intersection formulas hold, either on the case theoretical level for the motivic churn or on the homological level for the normalized Hirzebruch class. On the case theoretical, so here are the correction factors coming from the normal bundle. On the case theoretical level, this is really a tensor product of classes, and in the homological angle, this is really capping with a homology class. So this is a basic missing formula that the calculus, which one would expect, exists now for all 5 characteristic classes. And if with this theorem, I would say the basic calculus is completed, and the time is ripe to apply this to many, many applications. But this is not what I want to present today. Today, I just want to explain this result is true. So the expected intersection formula holds under this non-characteristic assumption, which I also used some years ago for the Churn class story. It also works in this context, but the price you have to pay again, you have to formulate this in the Hodge version or with Purvis sheaves. This non-characteristic does not in general make sense on the motivic level. So you have to be a little bit careful if you want to figure out what's the right formulation of this condition on a motivic level. Okay, so this is the basic intersection formula which holds under good conditions. So let me give 2 important applications directly of this intersection formula. So the first application is to an intersection formula. So we have an ambient space, and we can look at the diagonal embedding, and we take 2 pairs of coefficients, m and m prime, and we want to compare the intersection of these characteristic classes. So here, this d upper Schwieg is just a refined intersection of the characteristic class of 2 coefficients, and this is classically Lefschetz has done this. So how do you intersect in homology? You take first the cross product, and then you pull back or make a refined pullback by the diagonal. This is just the classical viewpoint of Lefschetz. And this formula tells you, under a suitable condition, the refined intersection of characteristic classes just corresponds to the characteristic class of a product, of a tensor product here, up to a correction factor. And once you have this for the motivic level, for the motivic Churn class, you will also have this for the Hirzebruch class transformation. But this, because there was not enough space on the slide, I don't present here. Another interesting application of this intersection formula is that it allows me to prove a weak version on our conjecture on the agreement of the L class of a singular space with this normalized Hirzebruch class of the intersection homology complex evaluated at the parameter y equal to 1. So that was the conjecture I presented in the introduction. And here we can now prove this conjecture, but a little bit less. We can't prove this in the homology of X. So we expect that this formula is true for X, and X should be here embedded in a projective space. So this is a singular projective variety. We can't prove this formula in the homology of X, but if we push forward this into the ambient homology of the projective space, then this expected formula is true. So this is a strong support that one should believe this conjecture is fine. Still, it is not proved in general, but at least this weaker version works. And why we can prove this? Because this is a proof by induction. So it's a classic Lefschetz technique. So you slice by intersection with a hyperplane. And the good thing is, here, the generic hyperplane will be a transversal to the witness stratification. So I can apply my formula here to the Hirzebruch class. And the other thing is, on the other side, you can apply a similar formula for the L class, because that was the formula proved this year by Markus Bannagel, that L classes behave nicely with the expected correction factor for transversal intersections. So you can do this by induction, and then you see if you make this proof by induction, what you lose if you intersect with H, with the class of H again, you lose the top power. So all other coefficients you would like to compare, the homology of a projective space is just a polynomial ring or a free group. And you see, you just move this coefficient you want to compare in 1 degree. And if you intersect with a hyperplane, you only lose the top power. This will be lost if you intersect. But the top degree here is the class which corresponds to a point class. And this is the degree of the L class and the Hirzebruch class. And the degree was already known before by the Hodge index theorem of Saito. So that is why in the end here the induction proof will work, because on the L class side we use Markus Banaghel's formula. On the Hirzebruch class side we can use this formula now. And for the induction step, only the degree 0 piece will be moved out, and the degree 0 piece was already known before to be true. And then we get this nice application to this conjecture on comparing L classes with Hirzebruch classes. And in principle, these are the two main applications I want to show you directly for selling the theorem. And maybe my last slide is just for the experts in the audience to see how this non-characteristic condition comes into the proof. So this is just only for experts how to prove this theorem. So what is behind? So what is used for this Gaussian map with intersection with submanifold is the construction of Verdier, the construction of the deformation to the normal cone, which is used for the definition of the Gaussian map. And because these characteristic classes, motivic, Churn, and Hirzebruch classes, commute with nearby cycles in the way I presented, from this you can deduce that they also commute with Verdier specialization. So Verdier specialization produces in the end some information on the normal cone, which sits inside this cotangent, this conormal boundary. And the claim is you also can use the Verdier-Riemann-Roch for the projection of this conormal boundary, because this is a smooth map. And if you use Verdier specialization and Verdier-Riemann-Roch, you only have to show the following. This is, of course, something I cannot explain today, but that is the trick which is behind this. So now you need a deep property of microlocal sheaf theory. So what one in the end has to show is that the Fourier-Sate transformation, so the Fourier-Sate transformation you can find in the book of Shapira on sheaves on manifolds, is a transformation from conic sheaves on the tangent on this vector boundary to conic sheaves on the cotangent boundary. So this transformation head is a kind of Fourier transformation for constructible sheaves going to the dual boundary. So here we now on the conormal boundary, and I claim, without explaining this in detail, the only thing you need to check is that the support of this Fourier transformation of the Verdier specialization is sitting in the zero section. If you can show this, then by the other results, one can show this formula. So this is the key technical thing to show. And how is this be proved in the end? This Fourier transformation of Verdier specialization is something which Kashiwara Shapira in their book call the microlocalization. That is a very, very complicated operation on constructible sheaves. And for complex constructible sheaves, this is really the same as the Fourier-Sate transformation of the specialization. And in the book of Kashiwara Shapira, they prove a general estimate that the support of this microlocalization is always sitting in the intersection of the singular support of the original perverse sheaf or general sheaf intersected with the conormal to the submanifold. And now you see where this non-characteristic condition comes in. I want to show that this support is in the zero section, and I know it's always in sit here. But now the non-characteristic condition means that this guy is sitting in the zero section. And then one can apply the estimate of Kashiwara Shapira to conclude with some general machinery that the expected formula is true. And then you see here's a lot of deep microlocal sheaf theory behind the proof of this formula. But for the calculus and for using this formula, this microlocal sheaf theory is not needed at all. So I think here my time is over. And I want to thank you for your attention to my talk. And more important, of course, is I want to congratulate to the South Carolina wonderful conference on real and complex singularities for 30 years already. And I hope, of course, it will continue at least for the next 30 years. Thank you.
Okay, thank you very much, Professor Jörg Schürmann, for this very nice talk. Let me see if are there some questions. I ask you kindly some patience. I think.
Oh, it's fine. And the subject is very complicated. I don't expect questions.
Okay. Just a moment. Are there some questions? Yes. Nivaldo Grulha Jr. Could Milnor class carry some information about this nearby cycle?
No, the Milnor class is of course for the Churn class story, but there's also a kind of Milnor class for the other characteristic classes, for the Hirzebruch classes, which is just more complicated, but has a very similar picture. Milnor classes are related to vanishing cycles. So nearby cycles see the nearby fiber, and as I explained, they are very nice behaved. For example, for Churn classes, this is a specialization result of Verdier. And what you would like to compare is you want to compare it with a restriction. So if you go to a hypersurface, for example, you have two sorts of restriction. You can pull back, this is nearby, and these are different. And that the formula is not true that measures the difference between these two things, nearby and special fiber. And the difference between nearby and special fiber, that is what the vanishing cycles are using. And this even works with this Verdier specialization for higher codimension, where I introduced a kind of generalized vanishing cycles. And they have to do with Milnor classes. But in my talk today, this is the situation where the Milnor class is vanishing. So if I have this non-characteristic condition, no vanishing cycles are there, and no Milnor classes are there, and then the formula is true.
Okay. Okay. Is there another question from Nivaldo? Is the Milnor class also a functorial class? Does it make sense look for it commutative diagram with these other characteristic classes?
The Milnor class has some functorialities. For example, Shoji Yokura had worked on these kind of things. So what is, for example, very easy is the Milnor class commutes up to the expected correction factor with smooth pullbacks, for example. What is more complicated is how Milnor classes behaves under cross products, for example, or push forwards. So then you need stronger conditions. But they have some properties, but the problem is the Milnor classes are not always functorial. What is functorial are the specializations in nearby cycles. And the vanishing cycles are not as good behaved because then you have to compare with the restriction. And restriction is not always functorial. That really depends on the context. But usually with this machinery I presented, one can expect even many formulas for Milnor classes using this language of this calculus.
Okay. We have another question by Brian Hepler. Should we picture non-characteristic pullbacks along an inclusion as an inversion of normally non-singular inclusion for non-ICs?
Yes. So normal non-singular inclusion is a kind of language introduced by Goreski-McPherson, especially for intersection homology, to get the functoriality for intersection homology. And this normally non-singular inclusion is a kind of follows also from transversal to a witness to application. And this is more a topological substitute for transversal intersection, which is designed, for example, to fit with L-class story. And this is the condition which Markus Banagel for the Gaussian map in L-classes use. And this non-characteristic condition is a kind of microlocal analog, but going to another side. You should see both as generalizations of transversal to a witness stratification, but both go into different directions. So the one uses a kind of topological tubular neighborhood. This is normally non-singular. And this one, what I presented here, is a microlocal analog in some sense.
Okay. David Trotman, what is a reference for your previous use of the non-characteristic condition that you mentioned?
I'm not quite sure if I understood this question correctly. So the difference the result I wanted to sell today is that these non-characteristic pullback formula also works for motivic Churn and Hirzebruch classes. And for the Churn class story, I proved this some years ago and presented this in this wonderful conference in Merida for Pepe Ciada's 60th birthday. And the article is published in the volume to this. And the new news of my talk today is the same result, which is more complicated microlocal sheaf proof, also works for motivic Churn and Hirzebruch classes. And the proof is very different from the proof I've given for Churn classes, which used at that time characteristic cycles. And this does not work for motivic Churn classes. So one needs a new proof.
Okay. Shipping Zhang asking, as application, you give an example for the pullback to generic hyperplane. Is there some argument for generic hypersurface of certain degree, higher degree?
It works for all. So there's no. These are statements which allows any singular space no properties on the degree. The only important thing is transversality, or a similar statement like transversality. And the hyperplane was only used to fit this easily in this formula, but the statement that the formula works for any smooth hypersurface of any degree, as long as you have a kind of transversality.
And then any other questions or comments? So let's thank you again, Professor Jörg.
Okay, I thank the audience, and maybe we will meet in a moment in the coffee break.
Before we finish, I would like to remind you all that now, after this talk, we will have a web cough, and the next talk will be at 11:40. Okay, bye-bye. Thank you, Professor Jörg.
See you.
Thank you, you all. See you.
Hello, everyone. Good morning, good afternoon, or good evening, according to your region. So it's a pleasure to introduce Luis Renato Gonçalves Dias, and from Federal University of Uberlândia, and he will talk about bifurcation value of algebraic mapping and Jacobian conjecture. Go ahead, please.
It's okay, Armando?
It's okay.
It's okay? Okay, thank you.
I'm not sure if I introduced you. I mean, I already introduced you, but did you hear me?
Yes. Yes.
I can introduce you again if you want. Okay.
No,
good morning, good afternoon, good evening, according to your region. It's a pleasure to introduce Luis Renato from Federal University of Uberlândia. He will talk about bifurcation values of algebraic mapping and Jacobian conjecture. Please go ahead.
Thank you, Raimundo. So I would like to say firstly that I would like to thank the organized committee for the opportunity to talk about my work. This is an joint work with Francisco Brown of SCAR and with Jean Benato Santos from UFO. The plan of my talk is there. Firstly, we begin with the Jacobian conjecture. We remember some definitions and we will remember the Jacobian conjecture. In the second part, we remember the definition of a non-property set of a polynomial mapping. And then we discuss our first result about the Jacobian conjecture. In the third part, we speak about the bifurcation set of a complex polynomial mapping from Cn to Cp. And then the last part, we will discuss some relation between the bifurcation set and the Jacobian conjecture. So we begin with the definition, with the Jacobian conjecture. The Jacobian conjecture asks if you have a non-singular polynomial mapping, then F is an automorphism. So this is a problem, an open problem, proposed by Keller in 1939, and you have several problems and several reductions related to the Jacobian conjecture. For instance, we know from the result from Chern and Hirzebruch that if you have a non-singular polynomial mapping and F is an injective mapping, then F is an automorphism. So this result of Chern and Hirzebruch, in fact, is more general. He stated this result for algebraic sets, but here we will discuss only the case of Cn to Cn. And this is a reduction theorem to prove the Jacobian conjecture. So to show the Jacobian conjecture, you need only to show that F is an injective mapping. One reference about the Jacobian conjecture is the book of Van den Hens, where he discuss several problems and another reduction theorem related to the Jacobian conjecture. Related to the Jacobian conjecture, we have the notion of a non-property set of a polynomial function, polynomial mapping. We remember the definition here. So given polynomial mapping from Cn to Cn, we say that G is proper at Y if there is a compact neighborhood K of Y such that the pre-image of K under G is a compact set. and you will denote by Sg all the set of points at which G is not proper. And you code this set Sg by the non-proper set of G. The non-proper set is related to the Jacobian conjecture as follows. Given a non-singular polynomial mapping, it's well known that F is an automorphism if and only if F is a proper mapping. It means that the non-proper set is empty. Of course, that direct from the definitions, if F is an automorphism, then F is a proper mapping. Consequently, the non-proper set is empty. And to show the reciprocal, for instance, you can use the Hadamard theorem. Since F is proper, then from the Hadamard theorem, you have that F is an bijective mapping. Then you can use the previous reduction theorem related to the Jacobian conjecture to obtain that F is automorphism. So, just to fix the idea from this last comment, the Jacobian conjecture will be proved if you can show that the non-proper set is empty for any non-singular polynomial mapping from Cn to Cn. Related to the non-proper set, you have the work of Jelinek, one result from Jelinek. In fact, the theorem of Jelinek is more general, but you present here on simple version. So the theorem of Jelinek say that if you have a non-singular polynomial mapping, then the non-proper set of F is empty, or the non-proper set is an unruly hypersurface. One remark here is that from direct by the definition of the non-proper set, we have that the non-proper set is a semi-algebraic set. But Jelinek show more that the non-proper set is in fact an hypersurface, unruly hypersurface. Hypersurface means here that the dimension of the non-proper set is n-1. With this statement, we can discuss our first result. Before we remember the notion of irregular mapping. So given two algebraic sets, X and Y, a mapping G from X to Y is a regular mapping if G is the restriction to X of a polynomial mapping defined in Cn, and you say that G is B-regular mapping if G and the inverse of G are regular mappings. In this last case, we say that X and Y are B-regular sets. With this, we can discuss our first result. So given a non-singular polynomial mapping, then the non-proper set is empty, or it intersects all non-singular hypersurface Y being regular to C n-1, on which some non-singular polynomial H is constant. So this gives another property of the non-proper set, and I would like to remark here that it's easy to find sets Y with the properties of theorem 3. For instance, sets Y with the properties of theorem 3 includes, for instance, graphs of polynomial functions from C n-1 to C. Next, I would like just to give some ideas of the proof of theorem 3. So the idea, we start with Y, such that Y with the properties of theorem 3 such that the intersection with the non-proper set is empty. And we will prove that the non-proper set is empty. Before we will remember some general fact about the non-proper set, if you give a non-singular polynomial mapping from Cn to Cn, the restriction of F from the pre-image of the complement of non-proper set under F is on covariant mapping of degree D. This D is just the geometric degree of F, and since the complement of the non-proper set is on connect set in the complex case, we have this characterization to the non-proper set. So the non-proper set is just the points in Cn such that the cardinality of its fibers is less than D, where D is just the degree of this covariant mapping. So we start with the idea of the proof. Now we consider V just the pre-image of Y under F, and we denote the connect components of V by V1, Vd. So, then we prove that the restriction of F on each connect component of V are B regular mapping. In fact, since Y does not intersect the non-proper set, we have that F is anymore. Since Y is on simply connect set, we have that F restrict to each connect component of V is on B holomorphic mapping on each connect component. But with the result of Hrusak and Winiarski, we can prove that the restriction, in fact, is on B regular mapping. So here in this step, we use only the properties of Y, and from the hypothesis, from the age, we can construct a polynomial function such that this new polynomial function is constant on each connect component of V, and then you use the fact that age is on submersion by hypothesis to obtain that D equal to 1. With this and the characterization of the non-proper set, we obtain that F is on injective mapping. It means that the degree of the covariant mapping is 1. Consequently, we have that F is on injective mapping from the characterization of the non-proper set. Then you use the reduction result of Sink and Hrusak to obtain that F is on automorphism, which implies that the non-proper set is empty. So this is just an idea of the proof, and I'd like just to fix some ideas is that from the theorem 3 and the Jelinek result, you have that if there is a counterexample to the Jacobian conjecture, then the non-proper set of this example is on hypersurface such that intersect all non-singular hypersurface Y with the properties of theorem 3. Now I just like to say some words in the real case. As in the complex case, you can ask if your non-singular polynomial mapping is on bijective mapping. This is false. In 94, present a non-singular polynomial mapping from R2 to R2, that's not an invertible mapping. And also, I'd like to remark that if you have a non-singular polynomial mapping, not a non-singular, but as in the complex case, we can define the non-proper set for a polynomial, for a real polynomial mapping, in the same way that we will discuss in the complex case. Is directed by the definition that the non-proper set is a semi-algebraic set, and also, and I would like to say here that the theorem or theorem 3 does not hold for non-singular polynomial mapping. In fact, in the Pinchuk example, we have the intersection with the non-proper set with these lines, vertical lines. The intersection is empty. Consequently, ZC satisfies the conditions of our theorem 3, but we cannot conclude that F is an bijective map. So our theorem, the real case, does not hold. And the real case also will have a reduction result related to the non-singular polynomial mapping. So it's well known that you have a non-singular polynomial mapping, and the F is an injective mapping, then F is an bijective mapping. And to finish, I'd like to say that in the real case, you have also open conjecture from Jelinek. So Jelinek states that if you have a non-singular polynomial mapping, if the codimension of the non-proper set is greater than 2 or equal to 2, then F is bijective. This is an open problem. Just remember here that the non-proper set is a semi-algebraic set. Then you can talk about the codimension of the non-proper set. And more interesting is that Jelinek proves if you show the conjecture 2, it means the conjecture in the real case, then you will have the Jacobian conjecture in the complex case. So now I discuss a little about the relation between the bifurcation set and the Jacobian conjecture. We begin with the definition of the bifurcation set. So given a polynomial mapping from Kn to Kp, then you say that T is a typical value of F if there is a neighborhood U of Kp such that the restriction on the pre-image of this neighborhood under F is on infinity trivial fibration. And if T does not satisfy this condition, we say that T is a bifurcation value of F. And you denote by Bf the set of bifurcation values of F. And you call this set only by bifurcation set of F. So some words about the bifurcation set. You have that a complete characterization for the bifurcation set is open problem. In fact, we have a complete characterization only for a special case. Just to give some reference here. For instance, for functions on the complex over the real plane. In the complex case, you have a complete characterization from the works of Suzuki and Lee. In the real case, you have a complete characterization from the works of Tibar, Zaharia, and Costa de la Puente. And more recently, for the case that the fibers of the polynomial functions are curves complex or real curves, we have the works of Joyta and Tubar. In fact, we have more general characterizations for special case, for instance, from the works of Baranzinski, Grandjean, etc. So, our motivation to study the relation between the bifurcation set and the Jacobian conjecture is from the work of Lane and Weber. In 1994, Weber proved the following theorem. So, given a non-singular polynomial mapping from C2 to C2, if one coordinate function of f is on fibration, which means that the bifurcation set of a coordinate function of f is empty, then Lane and Weber prove that f is an automorphism. I'd like to remark here that the proof of the Theorem 6 from the works of Lane and Weber use the Abian-Camus theorem. In fact, the theorem follows by the Abian-Camus result. With this theorem, Lane and Weber proved that the Jacobian conjecture in C2 can be reaffirmed in the following way. Reaffirmed means that the Jacobian conjecture for n equal to 2 is true if and only if this conjecture is true. So the conjecture presented by Lane and Weber is the following. If you have a polynomial function from C2 to C, if the bifurcation set of F1 is not empty, then for any polynomial function from C2 to C, you have that the mapping F1, F2 has a critical point. I'd like to remark here that if the Jacobian conjecture is true, it's a directive that the conjecture 3 is true. This followed only by the definitions, but to show that conjecture 3 is true implies the Jacobian conjecture true. This follows from the Theorem 6. So one motivation of your work is to try to extend this theorem for any dimensions. In particular, we have obtained that the Jacobian conjecture for any n can be reaffirmed in the following way. If we start with a non-singular polynomial mapping, capital F here, from Cn to Cn-1, it means that all the fibers are curves, smooth curve. If the bifurcation set of capital F is not empty, then for any polynomial function, H, you have that the mapping F(H) has a critical point. So, as before, if the Jacobian conjecture is true for n, then the conjecture 4 is true, and this follows directly by the definitions and the statements of the conjectures. To prove that the reciprocal means that the conjecture 4 is true, then you have the Jacobian conjecture. This follows by the next two results. It's just this also means that the implication conjecture 4 implies the Jacobian conjecture, follows by the next two results. These results is for non-singular polynomial mapping F. We start with a non-singular polynomial mapping from Cn to Cn, and suppose this is a topological condition, and you suppose that the connect components of the fibers of capital F out the bifurcation set of capital F are simply connected. So this is a topological condition, and this mapping capital F is just the mapping F by removing the last coordinate function of F. Then, with this hypothesis, we have that for any algebraic set containing the bifurcation set of capital F, this inclusion holds. Here, pi is just the canonical projection. Of course, we can change the definition of capital F by removing another coordinate function of F. Then we need to replace the projection here. And with this theorem, we can prove also the following theorem that is related with the Lane-Weber theorem. If you have a non-singular polynomial mapping, and if the fibers of capital F out the bifurcation set are simply connected, again, a topological condition, then F is an automorphism. In particular, we obtain for any dimension on generalization of the Lane-Weber result. So it means that for any non-singular polynomial mapping, such that the bifurcation set of capital F is just the same mapping here, defined in the same way, then F is an automorphism. So just some ideas of the proof of theorem 7. We remember here the theorem 7. So we start with a non-singular polynomial mapping, and we have this topological condition. And you want to show this relation between the non-proper set and the bifurcation set. Okay, so again, we remember this general fact for any non-singular polynomial mapping. We have that this restriction is on cover mapping of degree D, and D, as we have said, D is just the degree of the mapping F. And since the complement of the non-proper set in Cn is connected, you can describe the non-proper set in this way. Here, it means that the non-proper set is just the point in Cn such that the cardinality of its fibers is less than P. So now we start with the ideas of the proof of theorem 7. You fix an algebraic set such that this algebraic set contains the bifurcation set of capital F, and you set the complement L, we set L as the complement of the algebraic set Z in Cn-1. Then this is a connect set, and since the L does not intersect the bifurcation set of capital F, we have that the restriction of capital F from the pre-image of L under capital F is on local trivial fibration. This is found by the fact that Z contains the bifurcation set of capital F. Then, since this is on locally trivial fibration and the L is on connect set, we have that there is S, a natural number S, such that the fibers for each Y in L has exactly S connect components for each Y in L. The idea is to show that S is equal to D. So with this, we take any Z in the pre-image of L under pi. L, remember here, and pi is just the projection. Then this means that pi Z is an element in L. From the previous step, you have that the fiber has S connect components, V1 into Vs. And from the hypothesis on capital F, we have that each connect components here are simple connect set. And more, the dimension is 1. So each connect component here is homomorphic to C. Then we use the next coordinate function of small f, and you prove that the restriction of Fn on each connect component of V is on B regular mapping. In fact, this B homomorphism mapping is formed directly by the conditions, and you use the Hoseki and Werniansky theorem to show that this is on B regular mapping. Consequently, for any Z this in the pre-image of L under pi, we have that the fibers on small f has exactly S points. And since this set is an open set, we have that this set intersects the complement of the non-proper set of F. We obtain that S equal to D. Remember that L is an open set, just here is the complement of an algebraic set. So L is an open set. The pre-image of open set is an open set. Consequently, the intersection of this opening set with the complement of the non-proper set is not empty. Consequently, S equal to D. Consequently, by the characterization of the non-proper set, we have that the non-proper set is included in the pre-image of Z under pi. Which finish our proof is just this we want to prove. To finish, I just only to show an application of your result. We have a nice theorem from Bass and yours that which says that the Jacobian conjecture in all dimensions follows if you can prove that for any n, the non-singular maps of the form I plus h are injective mappings. Here, I is just the identity mapping, and the h is a homogeneous polynomial of degree 3. So this is a very nice reduction of the Jacobian conjecture. In particular, Hilbert's analytic form classified all the non-singular polynomial mappings of the form I plus h for n equal to 4, and he obtained 8 families of mappings of this form. Then he proved the bijectivity of each family by using a result of Vandermonsen. Essentially, the idea is to use the result depends on the Bellner basis of which is related with the coordinate functions of the families. And the remark I would like to say that you can check the simple connect of the fibers of each family in the Hilbert's classification. Consequently, we can use the theorem 8 on each family to show that each family is a bijective mapping. Of course, the hard part in the Hilbert's is the classification of all polynomial mappings of the form I plus H. But maybe our result can be useful in this to conclude that these mappings of this form is a bijective mapping. So it's just this I'd like to say. Thank you.
All right. Okay, thanks. Thank you, Luis Renato. Very nice talk. Please thank the speaker where you are. Just grabbing.
Thanks, Simon.
So let's wait just a little bit to see if someone will send us some question. But I just wanted to ask you, in low dimension, is it possible to use the Newton polyhedron at infinity of your coordinate functions, of your mapping as you want, to control such a bifurcation set? So what can you say about that?
Yes, there is some results about that in the real and in the complex case, and you can use the Newton non-degenerate to control the non-proper set. You have some works in this direction. For instance, the real case, you have the work of Bivel-Sina. In the complex case, you have one result with Tibar, Chen, Takeuchi, and you also have one result from Green in this direction. It means we use Newton polyhedron to control the non-proper necessity of the polynomial mappings to obtain the automorphism. We have some works in this direction.
Okay. Nice, thanks. So Alexandre asked, how difficult is verify that fiber of a Hilbert map? I don't know if I understood Alexandre Fernandez's question. But
yes, I understand.
Did you get it?
Yes, I understand. In fact, it's very easy. You can see the mapping, and you need to check that the sim connect for F1, F2, F3, for instance, and it's direct after the classification of the hubs, but it's really direct. Of course, the classification is very difficult, but after the classification of the hubs, it's easy to verify the connect components, that each connect components of the fibers are simply connected.
Okay, thanks. There is a second question here asked by Daniel Duarte. Can you hear me, Luis Renato?
Yes, I can.
Okay. Daniel Duarte asked what fails on the invariant H order for dimension x greater than 2. I'm not sure if you got.
Just a second. Can you repeat, please, the question?
So let me see if I can get to the question again. So it's, I'm not sure if he is asking such a question for you or if he's just chatting. Okay, no problem. Sorry about that. So Cidinha said, very nice talk. Thank you, Luis Renato. So she's asking a question. Do you believe that the Jacobian conjecture is true? Very tricky question.
Yes, I think so. I think so. The Jacobian conjecture is true, but no idea to prove.
Okay, nice. So let me see if we have more question here. Maybe nothing else. All right. Good journey. I think it's a very nice problem to pursue. And let's thank again the speaker where you are.
Thank you, Raimundo. Thank you.
Okay, Luis. Thank you very much. Thank you very much for your nice talk, and see you soon. Bye.
Bye.
Hello everyone. On behalf of the organized committee, I thank everyone who attended today's plenary talks. Now, I am pleased to present today's parallel talk. At 2 p.m., we have Vyacheslav Sedik at the National University of Oil and Gas. At 2:45 p.m., we have João Carlos Ferreira Costa, IBIUSI, and Reinaldo Roberto Rosa, INPE. 4 p.m., we have Leon Kushner, UNAM, and Konstantinos Kornoios. We would like to invite you to visit our poster section on the workshop web page here. Thank you very much. See you.